I should say generally this is kind of a talk in the spirit of a certain aspect of philosophy of physics, which is kind of to say stuff that everyone knows anyway, but hopefully to say it in ways that everyone hasn't quite thought of in that kind of way. So if I'm basically saying stuff to you that you already know, congratulations, you already have the right position. If not, then hopefully you can provide a little bit of clarity somewhere. Here's a kind of first stab at what you might call the central problem of the direction of time. Something like, given that the equations of fundamental physics are time symmetric or near as damn it time symmetric, and given that the macroscopic world is not even near as damn it time symmetric and seems to be near as damn it completely time asymmetric, what's going on? Okay, so, and here's a kind of very crude running through of what's kind of not far off a consensus line in how to think about this, and which also I think is not far off the right way to think about this, but which I think is worth looking at in a bit more detail. And it kind of says the answer to this central problem has got two components. Number one, what you might call some kind of assumption of dynamical typicality, which goes something like this. Look, phase space is really, really big, and it's carved up into macrostates which are really, really big, but they are unevenly really, really big. The larger ones, and we call those the higher entropy ones, are much, much, much larger than the smaller ones. So unless the dynamics in phase space or its quantum equivalent is ridiculously special somehow, we ought to expect that a basically pretty random point in phase space is going to make its way in fairly short order to the large regions of phase space, the high entropy bits of phase space, and unless it's got a really long time to play with, it's basically not going to find its way out. So if our measure of entropy or disorder or whatever is something like volume of phase space regions, and if phase space has got these geometry, and unless we're really unlucky, then that's what the system's going to do. It's going to make its way successively into bigger and bigger regions. And then the second half of the component says, well, hang on a sec, all of that reasoning was time symmetric, so somehow we better put something in to break that reasoning going backwards, and the reasoning is that we're going to declare by fiat that the initial universe was in a very low entropy state, a very small region of phase space, and because we've made that declaration, it means that now most trajectories that are going up in entropy towards the past aren't going to make their way into that special region, and so they're going to be disallowed. And so the ones that we're left with are going to be the ones which have the right kind of properties, which are lower entropy in the past, higher entropy in the future. Okay, and as I say, there's clearly something right about that, but I want to sort of worry away a little bit about some of the details of it. Here's one chunk of the worry. Basically, I'm going to give one concern for each aspect of that. So here's a concern about that kind of typicality principle, or that kind of framework of dynamical typicality, which is something like this. It's empirically not the case that we find most systems at equilibrium, witness the room. It's also empirically not the case that we find that systems reliably make their way to equilibrium quickly and stay there. If I take, say, a box full of equal mixture of hydrogen and oxygen, and I leave that box sitting on my shelf for quite a long time, it's going to happily stay a mixture of hydrogen and oxygen. But we know that's not the equilibrium condition, because if I drop in a match, then there will be a rapid equilibration reaction, and in fact, I'd probably be advised to do it from a safe distance. And in fact, even then, if you're kind of really serious about it, that system isn't at equilibrium either. At room temperature, that box full of steam, I suppose, at that point, would really quite like to be a box full of iron. Because thermodynamically, at these temperatures, it's thermodynamically favourable for the nuclei in hydrogen and oxygen to make their way into being iron nuclei. And we know that doesn't happen. Now, sure, it happens eventually. Sure, there's plausibly some principle that says that anything, if you seriously leave it long enough, will make its way to a maximum entropy state. But now, if that's our answer, we've kind of lost track of what we wanted to explain in the first place. We're not trying to explain some rather theoretical principle that systems, if you leave them for timescales which could be arbitrarily long, will eventually make their way to equilibrium. We're trying to understand clear time asymmetries in the here and now. So it seems that simply to have that kind of account can't be getting the whole story of the dynamical side of things. And there's also some reason to think that we can't have got the whole of what's going on with the low entropy past hypothesis assumption either. And the reason for that is something like this. Look, that assumption seems to say that the way in which we have knowledge of the very early universe has a profoundly different character from the way we have most other forms of knowledge. It seems to be something like it's a transcendental prerequisite for pretty much all of our knowledge that the universe was in some particular state, particular macro state very, very early on. And that seems kind of odd because there doesn't seem to be anything qualitatively different about the way in which we know about the Big Bang compared to the way in which we know about other facts in the past. So to kind of get a bit clearer on what's going on there, I want to actually pause on that thought and ask ourselves, okay, well, let's stop and think how we actually do in science work out what's going on in the past and work out what's going on in the future, and see if we can maybe use that as a lever to get a bit more handle on what's going on here. So here's a kind of line as to how to think about that. When we use our theories in science, and I don't just mean in fundamental physics, but in science right across the board, what we generally tend to have is equations governing the dynamics of the systems we're interested in, or increasingly the way we handle those equations is computer models handling the dynamics of the systems we're interested in. And what we tend to want to know is, okay, here's what's going on basically now. We'd like to know what's going on later, and we'd also like to know what was going on earlier. The way we work out what's going on later, fairly reliably, is we say, okay, what our equations are in the business of doing is giving us a map from what the conditions are now to what the conditions are in the future. And it's a determinate map. It's not necessarily a deterministic map. It doesn't necessarily say if the current conditions are X, then the future conditions will be Y, but it will at least determinately tell us, well, if the current situation is X, then the future conditions are going to be Y1, Y2 through Yn with probabilities P1, P2 through Pn. So if you like, the dynamics is deterministic at the level of evolving probability distributions. And of course, even this is a huge simplification because for the noisy situation we actually find ourselves in. But that's the kind of the spirit of what we're generally doing. And once in a long while, when we want to learn about the past, we do the same thing. Because once in a long while, the equations that govern the systems we're interested in have some kind of time symmetry. Either they're genuinely time symmetric, or more weakly, they're deterministic both into the past and into the future. So if you call that kind of normal means we use to work out the future prediction, once in a long while we find out about the past by retrodiction. And the classic example of this is how do we find out where the planets are? If I want to know where the moon is or where Jupiter is next month, I run a prediction. I take the current conditions, I plug them into the equations of motion for the solar system. I set those equations of motion up to allow for all the degrees of freedom that I can afford the computational power to allow for, and I run the equations forward and they tell me where the moon or where Jupiter is going to be later. And if I want to work out where Jupiter was earlier, say I want to compare notes with my colleagues in ancient history or something, I do exactly the same thing, but I replace the t with a minus t in the equations. Of course, that's almost always not what we do when we're working out what's going on in the past in any area of science. What we're normally in the business of doing is something that you might loosely call inference. We say, okay, well, suppose hypothetically that the relevant state of the relevant dynamical degrees of freedom 10 minutes ago or 10 years ago or 10,000 years ago or 10 million years ago was such and such. If that was the case, what would we have predicted if we did prediction using that data for the conditions in the here and now? And then we compare our predictions to what we actually see in the here and now, and we see if it matches up. In the kind of nice friendly case where it's all deterministic, if it doesn't match up, we say that was the wrong condition, let's go back, try another condition. In more realistic cases, then our prediction is probabilistic, and so we have to do some more delicate games to work it out. But either way, what we're basically doing is we're making a hypothesis about the early states, predicting forward and seeing where we end up. And it's not even particularly mysterious, at least on a surface level, why there's this kind of asymmetry normally going on in the way we use our equations to make predictions about the past and to make predictions about the future and inferences about the past. Because those equations, generally speaking, are manifestly time asymmetric. Generally speaking, those equations in various ways are irreversible. They're in the business of reliably telling us if the condition now is such and such, then the condition later is such and such. But they're not reliably in the business of telling us if the condition now is such and such, then the condition earlier was such and such. They just don't have that mathematical structure. And the obvious case would be equations, phenomenological equations governing systems going to equilibrium. The equations will fairly reliably tell you if the system's not at equilibrium, here's the time scale by which it gets to equilibrium. But if the system is at equilibrium, the equations tell you basically nada about when it reached equilibrium previously. And we're in the inference game rather than the prediction game if we're trying to work out what assumptions we should make about its earlier state. Okay, so at the surface level it's not problematic, but of course we think of science as a pretty unified business. We think that when we've got some phenomenological equations describing some higher level situation like what the solar system does or what my coffee does, those equations don't have a complete autonomy. They're not things that just sprang into existence independently. They're somehow things which can be derived from lower level things. Now, I should flag for honesty that that's occasionally been a bit controversial in various areas of philosophy of science, and I think the best way to describe the alternative controversial position is that it's wrong, and so I won't say any more about it at this point. But okay, that gives us a second stab at our problem. It's not sort of directly how do we reconcile the observed asymmetry of the world with the symmetry of the equations of fundamental physics. It's how do we reconcile the time asymmetry of most of the emergent higher level equations we use in science with the fact that they're supposed to all derive from some set of equations that governs the very, very small and that is time symmetric. Okay, so I should flag another possibility there. There's a straightforward way we might reconcile that, which is that we might say, okay, well, possibly what this tells us is a deep insight into whether the equations governing the microphysical world are themselves time asymmetric. And I think that's a very interesting and serious and well-motivated position, and George Ellis talked a bit about it a couple of days ago, David Albert's developed it, but despite the fact it's serious and well-motivated, I think it's also best described as wrong, and so again I'm going to put that aside. Okay, so that's a second stab at the problem, but there's still something slightly puzzling about it, because not only is it the case, why do we think that the equations of macrophysics and the dynamical equations of others of the sciences are somehow derivable from lower level physics and ultimately derivable from fundamental physics? Sometimes you get the impression that we think this because of some a priori confidence that the world must somehow be compositional in structure. That somehow it's just logically necessary that the things that govern the higher level degrees of freedom must somehow be derived from things that govern the lower level degrees of freedom. And I think that's reasonable enough, but I don't think that's the most powerful argument for why the higher level equations are somehow derivable from the lower level equations or follow from the lower level equations. I think the real insight as to why that is that in hundreds and hundreds and thousands of situations, we've more or less managed to do it. We have absolutely, by no means do we have the full story about all the various interrelations between levels of science, but it's also by no means that it's a profound mystery. And in particular, if you think about the kind of equations that govern macro-level phenomenological situations, and particularly I'm thinking of the kind of equations that govern statistical mechanical systems out of equilibrium, we don't, by and large, just guess those equations and draw them out of the experimental phenomenology. Very often, we somehow, I'll say derive, but at least construct those equations from microphysics. We have ways of taking lower-level physics, messing around with the equations of lower-level physics in a relatively well-defined and well-controlled way, and getting out of, as a result of that messing around, equations for higher-level physics which work pretty well. So that suggests here's a third stab at the problem. It's not just how do we directly explain the asymmetries of the world in terms of fundamental physics. It's not just how do we explain the asymmetries of macrophysics in terms of fundamental physics? It's how do we make sense of the methods we actually use to derive macro-level physics and fundamental physics, given that somehow those methods seem to have done the impossible. They somehow seem to have derived an irreversible situation from a reversible starting point. They seem to have derived an asymmetric situation from a symmetric starting point. Okay, but the problem as phrased that way is starting to get a lot more mundane, and the advantage of things getting more mundane, the disadvantage of things getting more mundane is they don't look quite so good in your impact statement. But the advantage of things getting more mundane is they start to look more tractable. Because the problem at the top looks like this kind of great sweeping philosophical problem. But the problem at the bottom now seems to be something that we ought to be able to get some headway at if we actually look at what people do, and we actually have a look at what the structure is of the methods we use to construct higher level equations from lower level, and kind of see what they're doing, how the trick is done. Okay, so here's a very kind of sketchy, schematic take on what I think is what's generally going on in these kind of situations. And I'm thinking here of things like how do we derive things like transport equations from statistical mechanics, how do we derive the kind of equations that govern the approach to chemical equilibrium, how do we derive things like the heat flow equation, how do we handle energy flow through the stellar atmosphere, etc., etc. So let's start by kind of just schematically how we think about the microdynamics. Or when I say microdynamics, I should say I'm kind of thinking of this very often as relative. When I say micro, I mean the lower level. When I say macro, I mean the higher level. We don't, by and large, start with the equations of the standard model and derive equations that govern traffic flow on the highway. We tend to do it in small steps. But the crucial thing that we're interested, of course, is what about when the microequations have the time symmetry and the macroequations don't? So that's the kind of situation I'm going to be thinking of. Okay, so here's a general way of thinking about it. We want to we're very often going to have equations, even at the micro level, certainly at the macro level, that are probabilistic rather than deterministic. So if we want to talk about the dynamics deterministically, we want to talk about how they are on a kind of space of probability distributions. So at the micro level, let's suppose I've got some state space and I've got some probability distribution over that state space rho, and I want to see what the microequations tell me about how to evolve that rho into the future. And very schematically, and this is the kind of thing philosophers can get away with, as equations go, this is not exactly technical. I've got some kind of general transition function, u, whose job it is to map the function, the density function at rho, which tells, at time 0, which tells the probabilities at time 0, into something that tells the probabilities at time t. And this thing in general I'm going to be able to run in either direction. And of course, if I could calculate this thing, then I could, well, this isn't true actually, but for the first approximation, if I could calculate this thing, I could use it to get the macro information direct. I probably wouldn't understand it, that's the sense in which it's not true to second approximation, but at least if my computer could actually handle this thing in full generality, I wouldn't need to derive macro equations to make macro predictions. But of course I generally can't. Here's what I think we generally do when we're deriving a macro equation from this kind of micro starting point. We have some kind of, call it a coarse graining rule. The coarse graining rule is a map from probability distributions to probability distributions. And the map's got kind of two features. One is it preserves the macroscopic level features of the probability distribution. If the probability distribution says there's a 32% chance that the density, the kind of macro density of the system is such and such, then the coarse graining doesn't change that number, or doesn't change it much. But the other thing the coarse graining generally does is it throws away a lot of information. I'm not going to talk much about dangerous words like information, so this is just to get a kind of heuristic idea. But I mean, to be clear about the kind of thing it normally does, what we normally do in the coarse graining is we're throwing away correlative information, or at the quantum level we're throwing away entanglement information. So here's a classic example. Suppose I want to understand the decoherence process by which some quantum system gets entangled with its environment, and as a consequence, kind of quantum interference phenomena inside the system gets suppressed. Normally what I do is I start off with the system in some density matrix state and the environment in some density matrix state. I evolve that system a little bit forward unitarily, and then I trace out, so I've now got the density operator that correctly describes everything that's going on in the system, and I've got the density operator that correctly describes everything that's going on in the environment, but I've thrown away the entanglement information that in principle you could get out by very subtle system-environment correlations. And then I iterate that process. I evolve the system forward a little bit more under the unitary dynamics, I get a little bit more entanglement, I trace that out, and I keep going. And normally in practice I take some kind of differential limit. Similarly, if I'm doing some kind of flow equation, I'll take some kind of distribution, in classical physics, I'll take some kind of probability distribution for some complicated multi-body system, which starts off not containing very much correlation between the various bodies. I'll evolve it forward a bit, which will generate various levels of kind of correlation to second order, between pairs of particles, triples of particles, quadruples of particles, sets of 10 to the 14 particles, and so on. And then I'll throw away some of that correlative information. If I'm being really crude, I'll throw it all away. If I'm being less crude, I'll throw it away to some higher level. And then I'll iterate the process. By doing that, I'll get a kind of recipe by which my coarse graining process plus my original microdynamics generates a macrodynamics. And let's be really clear, when I say generates, I mean this is a mathematical recipe which, if I apply it, gives me some equations. So I'm saying nothing at all here about the validity of this process. And let's ask what validity could mean here. Because I mean, validity clearly cannot mean that what I get out from the microdynamics is the same as what I get out from the macrodynamics. Just to be clear on that. Unless that coarse graining process is a real physical process, in other words, unless we're wrong about the macrodynamics, about the microdynamics, and sometimes the microdynamics really does something which at the probability level can be described as throwing away correlative information. Unless we're just wrong about the microdynamics, which I'm kind of ruling out as a possibility for the moment, then the microdynamics will predict that the system has an enormous amount of very delicate correlated information that the macrodynamics will not predict it has. So the theories are disagreeing in this way. There's no prospect of just deriving the fact that the macrodynamics are correct at the micro level. But they might be correct at the macro level. It might be that the microdynamics gets the same answer as the macrodynamics up to coarse graining. In other words, it might be that if I take the system and I evolve it, so because schematically this is time and this is phase space or something, the microdynamics says the system does this. The macrodynamics says the system does something like this, and then jumps, and this, and then jumps, and this, and then jumps, and this, and then jumps. At the end of that process, the microdynamics say the right probability distribution is here. The macrodynamics say the right probability distribution is here. Here is not the same as here. But if the coarse graining map takes you from here to here, in other words, if the coarse graining map takes you from the output of the microdynamics to the output of the macrodynamics, then the macrodynamics get the macro facts right. It doesn't seem an unreasonable thing to ask of macrodynamics. If you want to get the microdynamics right, do the microdynamics. If all you want to know is the information about the macro state of the system, then it seems okay to get the distribution right up to coarse grading. So we might hope that what's going on is that we can get away with coarse grading in this sense. And we might say that an initial state rho is forward compatible with a particular coarse graining if applying the microdynamics and then coarse graining gives you the same answer as applying the macrodynamics direct for reasonable lengths of time. Anyone who knows anything about the Poincare recurrence theorem will know that the idea that this could hold for all lengths of time is not going to be possible. But nothing about the Poincare recurrence time rules out that it holds for the kind of timescales on which we use normal macrodynamics. Okay, so maybe we can get away with it. And furthermore, it kind of feels fairly plausible that we can get away with it, because we might well think, well, okay, what we're doing is we're throwing away really high-level correlative information. But the actual microdynamics is generally pretty local, and it's going to be pretty difficult, we might kind of intuitively think, for the dynamics that governs the kind of bulk properties of the system to really care that much about whether there's delicate correlative information between what's going on here and what's going on here, or what's going on between this particle and what's going on with that particle. And so we might think, okay, this is just a reasonable assumption to make. And so we might be inclined to make what you might call a bold dynamical conjecture. Maybe, for reasonable coarse graining rules, all initial states are forward compatible with the coarse graining. And if the bold dynamical conjecture held, we'd be laughing, everything would be fine. Unfortunately, there's a fine line between boldness and stupidity. And the bold dynamical conjecture strides boldly across that line. And there's a reason for that. And the reason comes down to what you should always have in the back of your mind whenever someone tries to pull a fast one on you with statistical mechanics, which is, unless you put some time asymmetry in, you ain't going to get any time asymmetry out. I haven't made it explicit, but it's pretty clear the kind of coarse graining rules I'm using don't violate time symmetry. It's also pretty clear that, in some appropriate sense, it's also pretty clear, well, it's clear by fiat that my microdynamics doesn't violate time symmetry. So if I'm going to generate a macrodynamics going forward by evolve forward, coarse grain, etc., then I can also generate a macrodynamics going backwards by evolve backwards, coarse grain, etc. And it seems pretty clear that if the bold dynamical conjecture holds going forwards, it's going to hold going backwards. So that ought to say that the backwards macrodynamics ought to give the same answers as the microdynamics. And now we're in quite a lot of trouble. Because if the macrodynamics are forward and if the initial state we start with is forward and backward compatible with the microdynamics, something like this should be possible. Here's what happens under the microdynamics. I evolve the system forward to here, and I evolve it right back again. Here's what happens if I evolve it forward under the macrodynamics, and then backwards under the macrodynamics. I go something like that, and now I just keep going. And now I'm kind of just somewhere completely different from where I should be. And I mean, you can see this directly if you think about something like a heat flow equation, or anything which has, say, some kind of thermodynamic entropy that goes up. The forward macrodynamics is going to say entropy goes up going forward. The backward macrodynamics is going to say entropy goes up going backward. And so if I apply the forward macrodynamics and then the backward macrodynamics, I get to somewhere with a much higher entropy than where I started. But according to the bold dynamical conjecture, then the compatibility means that I should have stayed exactly where I started. Okay, so much for the bold dynamical conjecture. But there was something kind of in it, something reasonable in it, I think. Those kind of hunches and intuitions that somehow the quality of information shouldn't generically matter seems to have something reasonable going on. I mean, let's ask ourselves, why does it turn out that if I apply the forward dynamics for a bit and then try to time reverse, I don't get something that, I don't get back to where I started if I keep applying the backward coarse gradient dynamics? And the reason is pretty clear. It's that actually, if I evolve my system forward some way, and then I try to time reverse and run it backwards, actually those correlations were not just innocent, because in a system that's evolved forward, say, to a higher entropy state, those correlations are exquisitely delicately set up such that they conspire together in just the right ways that the microdynamics will deviate from what would normally happen if I tried to just go backwards using the coarse grading. You know, it's just the case that the particles are arranged so this particle's coming in at just the right time to bounce off that particle and to go back to the kind of small corner of phase space where everything started, or something like that. So if we were to use initial states which are exquisitely delicately set up to have properties like that, then we're going to be in trouble. But that seems to have a fairly simple solution. Don't use states like that. That's, what seems to be a more reasonable dynamical conjecture is that probability distributions are going to be forward compatible with reasonable coarse grading processes for reasonable times, provided those probability distributions are not conspiratorially carefully set up with a delicate tangle of correlations. And in particular, it seems reasonable enough to suppose, and we're at the level of kind of heuristics and arm waving here, but it seems reasonable to suppose that if I start off with a reasonably simple probability distribution, simple being something like I can't describe it in some, I could describe it in some reasonably straightforward way, and I better say that also the reasonably straightforward way I describe it had better not be start with something simple, evolve it forward a bit till it develops some correlations and time reverse it. But if I have something that's reasonably simply described, for instance, a probability distribution that's reasonably close to uniform over a region of phase space, or that varies slowly over phase space, or its quantum equivalent, then it seems reasonable enough to suppose that a distribution like that is going to be forward compatible. And that starts giving us a dynamical conjecture that's a little less bold, but a little more reasonable. Call that the simple dynamical conjecture. For reasonable coarse grading, all reasonably simple initial states are forward compatible with the coarse grading. Where do I go from here? From here, fine. Okay, so there's a problem there as well, which is something like this. The condition of being reasonably simple, even though it's rather vaguely set up, is fairly clearly going to be time reversible. So if I start with a reasonably simple probability distribution and I run it forward under the macrodynamics, in other words, I evolve it, coarse grain it, evolve it, coarse grain it, everything's happy. We reckon that dynamics is going to be forward compatible. But if I run that distribution backwards from the initial time to still earlier times, it's pretty clear that's going to be backward compatible with the dynamics. In other words, my derivation of the forward dynamics is going to be right for times after my initial distribution and wrong for times before my initial distribution. So I can only get away with saying I'll understand the derivation of the macrodynamics by postulating a simple probability distribution if I'm only interested in explaining the macrodynamics for times after the point at which I make the postulate. And then, of course, and this I think is the kind of, if you like, the kind of brazen genius of something like the past hypothesis, I say, well, I can solve that problem very simply. The way I'll make sure I don't get the answer wrong for times earlier than the point at which I make this postulate is I make sure there aren't any times earlier than that postulate. If I decide I'll assume the probability distribution right now is reasonable, then I'll fail to recover the empirically confirmed macrodynamics for times earlier than that. If I make it 1,000 years ago, I'll fail to confirm them for periods before 1,000 years ago. If I make it at the beginning of time, it feels like I'm safe. Now, in this audience, of course, I'm not remotely safe, but at least for the physics of the observed classical universe, I'm looking reasonably okay. Okay, so to summarize the picture we get from that, what we seem to need to get out, at least kind of qualitatively, at least have a fighting chance to derive the macrodynamics we have, is some combination of a reasonable sounding conjecture about the way the dynamical processes in our world work, i.e. you have to set up your correlations damn carefully in order to get behavior that doesn't behave well under coarse graining, and an assumption that the probability distribution or equivalently density operator, or in quantum mechanics possibly just the original state, was not carefully and delicately set up. It was set up in a relatively simple way. Now notice that we've got a slightly different past hypothesis on the table here from the one we started. The normal past hypothesis that people like David have talked about is a past hypothesis on the macrostate. It says that the macrostate of the early universe was some particular macrostate, which inter alia was a low entropy macrostate, although people are right to stress that they don't just mean it must be low entropy, they mean it's some particular macrostate. What we've got here is not a condition on the macrostate at all, it's a condition on the micro details compatible with that macrostate. The kind of line I've been saying is, it hopefully gives the result that I'll get the equations of the macrodynamics right, provided the microstructure of the early universe is not kind of tangled up and complicated. Getting the macrodynamics right doesn't require the macrostate of the universe to have any particular features. Now, of course, that isn't to say we don't need to know things about the macrostate of the early universe to get the actual world right. Of course we do. But what I think we have is some kind of division of labour. By assuming that the initial state has a fairly simple microstructure, we can guarantee that the equations that we use at an emergent level in macrophysics have the right kind of irreversible properties. And then those laws, plus the assumption that the initial macrostate has a low entropy, and lots of other assumptions about the initial macrostate, which are more or less on a par with that assumption, that will suffice to tell us that we get the actual macroscopic features of the observed world right as well. So to go back to the kind of framework I was talking about earlier, once we know that we're justified in using the kind of irreversible macro equations we use, then the way in which we learn about the Big Bang is the ordinary kind of inferential process we use in physics in general, in science in general. The transcendental thing, the thing that we're not going to get out from the ordinary inferential process, on the kind of line I'm exploring here, turns out to be a condition on the microstructure of the early universe, not on the macrostructure of the early universe. Okay, so just to finish there, where on that kind of account did the asymmetry come in? It didn't come in the direct assumption that the early universe had a low entropy. It simply came in the assumption that the early universe had a simple structure. If the universe were closed and in a nice simple cosmology where there's no bouncing and no internal inflation and so on, then of course the other end of the universe would have a very, very complicated structure. As a consequence of all that, it would have a higher entropy, but what's doing the work there, I think, is the simplicity assumption about the microstructure more than our assumptions about the macro features like low entropy of the early state. Okay, I'll stop there.